So when we're measuring distances, we're measuring length, and we kind of interchangeably use length, width, height. And there is really no convention for which dimension of this rectangle is the width and which is the length. I mean, height, we typically will be in this direction, but some people like to call this the width, and some people like to call it the length, and there really is no right and wrong about that. When we're measuring all the way around the outside of a figure, we call that the perimeter, and it's still a measure of length, usually a measure of, at least like in a square or a rectangle or another form like that, a measure of several different lengths added together. In the case of a circle, it's not different lengths added together, it's all the way around the outside. And in that case, we call that measurement circumference. We talk about the circumference of a circle. So looking at this shape here as an example, if the lengths are given to the nearest centimeter, what could the value of the perimeter of this shape be? Well, the most obvious thing is it could be 1 plus 2 plus 1 plus 3 plus 5, which is 3, 4, 7, 12 centimeters. But if you look at this, it does say lengths are given to the nearest centimeter. I don't know how precise that really is. If it's to scale, so this is another thing that we'll often see in diagrams. It will say something like not to scale. And that's really just meaning that they don't want you to measure things and read values off the diagram. Sometimes people will do it to be deliberately misleading in a diagram, but I would hope that we're probably not doing that with elementary school students. However, if these were measured imprecisely with a ruler that only had centimeters, and they were done roughly on this scale, you might notice that really, this line here is not twice as long as this line here. So there's probably some imprecision coming in here. Who knows, if I went in and measured with a ruler that has millimeters, in other words, tenths of centimeters on it, I might find that, well, this is closest to 1 centimeter, but it's not that much shorter than the one marked 2. So maybe this one is actually 1.4 centimeters, and this one is only 1.7 centimeters. And that one could be like 1.2 centimeters. And then maybe this one is 3.1 centimeters, and this one is 5.2 centimeters. Those are certainly all measurements that could lead to a diagram being labeled with these kinds of values, the 1, 2, 1, 3, 5, especially in elementary school. And if that were the case, then working with tenths of centimeters, we might say that the perimeter is 1.4 plus 1.7 plus 1.2 plus 3.1 plus 5.2, which is 3.1, 4.3, 7.4, 7.6, so 12.6 centimeters. Or if we were doing something like having them measure all the way around the outside with a piece of string, and then finding the length of the piece of string, in this case, they might measure that piece of string as 13 centimeters because now it's closest to 13 centimeters once they've added up all of those sides. So it is possible to get different answers, even if you're just working to the nearest centimeter, depending on how that measurement is done. If you're rounding all the values first, to 1, to 2, to 1, to 3, and to 5, you're going to get different value. You may get a different sum than if you add them up all first, like measuring around the perimeter with a string, and then measure that total. So speaking of doing this, measuring around the perimeter with something like a string, that's an example of the additive nature of measurement. So we will often measure different parts and then add them together and accept that that is the measurement of the whole. We apply it here in area. So if I'm interested in the area of this shape shown, what I will typically do, and this is pretty common in just about any elementary school workbook, is break it up into triangles and rectangles or squares that I can easily find the area of. Now, I think here, if I were to do this, I would run into trouble because I can't find the area of this shape here. So I'm going to make sure that I draw my line here. So now I have only triangles and rectangles, and I can find 1, 2, 3, 4 separate areas and just add them up. So how would this look? Well, let me add in a little bit of graph paper because most commonly in elementary school, this is how students are going to find a shape like this, the area of a shape like this. They're not going to be using formulas. They're most likely going to be drawing it or having it presented to them, drawn on a graph or dot paper. So let me try to replicate it roughly here. Okay, I just took a moment off screen to draw this because I was having some trouble fussing with it with my pen. So I'm just going to measure or calculate or count, depending on what level the kids are at, each of these areas separately. And for area 1, it's a triangle. You don't necessarily need the formula for the area of a triangle to see that you have half, whoa, this is not good, to see that you have half of a square here and half of a square here, so that's a full square. And then a full one there makes 2. And for area 2, we can see 1, 2, 3, 4, 5, 6 squares. For area 3, this one's a little more difficult to count up because the pieces aren't exact halves. You could use the formula, half of the base, which is 4, times the height, which is 2, and that gives me 8. But you could also see it for younger kids as half of this rectangle without explicitly using the formula half times base times height. That rectangle you can see is 8 squares, and so half of it is 4 squares. Same thing here in number 4, although I think this is one where we can say 1 half, 2 halves, so 1 whole, a second whole, and then 3 4. So if I add those all together, 2 plus 6 is 8, plus 4 is 12, plus 4 is 16. I have 16 squares. Now, squares is a non-standard unit because it depends on the size of the graph paper that I'm using. In this particular case, if this was in a book where it was made clear that this was 1 centimeter by 1 centimeter, then you could say 16 square centimeters, but not necessarily, unless that was the case. All right, so here we're going to do a similar thing with perimeter, where we're adding up different pieces. I have a piece that is half of a circle, and then I have 3 sides of this rectangle. And I know or I would know if I were an elementary school child at an age being given this problem, that the circumference of a circle is 2 pi r, and so the half circle will be 1/2 of 2 pi r, and 1/2 and half just multiply to 1, so this is pi r. In this particular instance, my r is the radius, which is half of this side length, and the side length is 4, so this would be 2. So this would be 2 pi. And this is assuming that the measurements are exact. So if the measurements are exact, I would have 2 pi plus 5 plus 4 plus 5, which is 14 plus 2 pi. And this is going to be I'm just going to write around 20.3. Well, that was assuming they were exact values. If they were made with a ruler that was marked in centimeters and no millimeters, all I can really say is that this 4 is somewhere between 3.5 and 4.5. And therefore, this radius here is somewhere between half of that, 1.75 and 2.25. And this 5 is somewhere between 4.5 and 5.5. So what would the perimeter be, or what would be a reasonable answer for the perimeter in this case? Well, it could be from as small as 4.5 plus 3.5 plus 4.5 plus 1.75 pi, 4.5 plus 3.5 plus 4.5 plus 1.75 pi, to as large as 5.5 plus 4.5 plus 5.5 plus 2.25 pi. And those range by quite a bit. I will write those in afterwards before I post it, and you can take a moment and add them up yourself, just that it's something I can't do easily and quickly in my head as I go. All right, the last thing I want to cover in this chapter is something that they do kind of obliquely, but they don't do it as explicitly as I would like.